Hi there. We continue this video series on integral functions, and we're going to talk now about the beta function. So we had spoken about the gamma function, and the gamma function we had actually seen depended on some integer n, and it was defined as the integral from 0 to infinity of x to the power n minus 1 times e to the power minus x dx. And we had derived a general result for this kind of function, and we had seen that this was actually equal to n minus 1 factorial. So this was the general result. So what we want to do now is define a new kind of integral function, that's the beta function. And how it's written is that we call it b, so b represents the beta function. And in the beta function, we actually have two numbers, whereas the gamma just had one n. Here we have m, and we have n. And the way it's defined is that it's the integral from 0 to 1. So it's not 0 to infinity, it's 0 to 1. And we have x, and this x is raised to the power m minus 1. So that's the first integer that you can see. And this is multiplied now by 1 minus x to the power n minus 1 times dx. So this is the beta function. It's a very useful function, and it's used in a variety of different ways. And how we can actually find a lot of use for it is if we derive a general result. So we had seen that with the gamma function, we have this general result where we can just say it's this n minus 1 factorial. So can we derive some kind of general function for the beta function in the same way? So yes, we can. And the way we proceed about doing this is by doing a substitution. So the substitution that we're going to do is that we're going to let x equal to sine squared theta. So that's the substitution that we're going to do. So if we just take the derivative, we see that dx is equal to 2 sine theta times cos theta. So we're going to substitute this in. So b, beta function of m and n, is going to equal to this integral, and we have to change the bounds. Okay, so x is equal to 0, that's the first bound, and when x is equal to 0, it can only happen if theta is equal to 0. In the same way, if x is equal to 1, we can only get 1 if theta is equal to pi over 2. So this integral goes from 0 to pi over 2. And now we have x to the power m minus 1. So it's actually sine squared to the power m minus 1. We have sine squared theta raised to the power m minus 1. So this sine squared, we can actually write it as this 2 is here on the outside, and this is raised to the power m minus 1. So we have to expand it out, so it's 2 times m, then minus 2. So we have sine to the power 2m minus 2. And this is with respect to theta. Now we have 1 minus x. So we'd also have to remember that sine squared is actually 1 minus cos squared. So this is 1 minus sine squared. So we have cos squared theta raised to the power n minus 1. So in the same way, we can just bring it in to the exponent, so it becomes 2n minus 2. And this is with respect to theta. So we have now transformed this particular integral to be in terms of sine and cos, and then we need to substitute in dx. So we just have to remember that dx is equal to 2 sine theta cos theta d theta. So we just put that in, 2 sine theta cos theta times d theta. We can do some simplifications. So this 2, we can bring it out of the integral. Then we have 0 to pi over 2. So here we have 2m minus 2, and then here we have 1. So it's 2m minus 2 plus 1 according to the laws of exponents. So that means we have sine of 2m minus 1 theta, and then it's the same with cos. We'll have cos 2n minus 1 theta d theta. So this is now our beta function converted into this form with this sine and cos. So what can we do with this? How can this help us to move towards some kind of general result? Well, it can help us to move towards a general result, but we have to make use of a special formula. So this types of formulas is covered usually when people are studying integration by parts in elementary calculus, and that formula is the reduction formula. So we need to make use of a reduction formula. There are several types of reduction formulas that's been developed for example, sine to some exponent, then cos to some exponent, etc. So the reduction formula that we're going to use is specifically the integral from 0 to pi over 2 of sine mx and then cos to the power n of x dx. And then what this is equal to is m minus 1 divided by m plus n times the integral from 0 to pi over 2 of sine m minus 2 times cos to the power n x dx. So how is this derived? Well, this is derived using integration by parts. So the technique that we would do is that we would split this sine, we would split it into sine x times sine m minus 1 x. So m minus 1 plus 1 gives us m, and then we would have times cos to the power n x. So we would now evaluate this using integration by parts. So we would integrate this term and we would differentiate that term. And then using the formula of integration by parts, we would get this result. So there's two results that we actually get depending on our approach. So this is the one result, and the other result is if we do the opposite. Instead of splitting the sine, we split the cos. So what I'm saying is that we have sine to the power mx, and then we split this cos in. So we have cos x, and then we have times cos to the n minus 1x. So in this case here, we differentiate the cos to the n minus 1, and we integrate this sine mx times cos x. And then when we do that, we actually get a different result. Well, it's not a different result in the sense that it's a different integral, but it just looks like it's in a different form. So the second result is that it's n minus 1 divided by m plus n times the integral from, again, 0 to pi over 2. And then now it's sine to the power mx times cos to the n minus 1 x dx. So I'm not going to do these full derivations here. These are quite elementary to actually derive. And once you split these terms apart and then apply integration by parts to these various terms as I've written, then we get these two results. So what we're going to do is we're going to use these two results. So maybe we'll call this 1 and we'll call this 2. So what we're going to do is apply 1 to our beta function as we had just written it now. This beta function of m and n, it was equal to integral from 0 to pi over 2. So that remains the same. We will still have the integral from 0 to pi over 2. And we have this 2 here as well. So if we apply this first result, we have m minus 1. So it's not m that we have, it's actually 2m minus 1. So we won't use m, we'll use 2m minus 1. So when we do that, we put in 2m minus 1, and then we have minus 1, and this is divided by m plus n. So it's not m and n, it's actually 2m minus 1 and 2n minus 1. So we substitute that in. Instead of m, we put 2m minus 1, and then we have plus n, and that's 2n minus 1. And now we have the integral. Let's not forget the 2, so there's a 2 here. So we multiply by 2 times this integral from 0 to pi over 2. And now we have sine of m minus 2, sine to the power m minus 2. So sine, and now it's actually 2m minus 1 here. So we have 2m minus 1, 2m minus 1 minus 2. So that's going to give us 2m minus 3, because we have minus 1 minus 2 gives us minus 3 times x. And then instead of cos n, we have 2n minus 1. So it's going to be cos of 2n minus 1 of x dx. So that is how we have just converted this beta function using this formula here. So what we're going to do is now we're going to apply this second equation to this integral that we have just written. So this integral within this square brackets, we're going to apply this second result to it. The reason why we're doing that is because you see that we have 2m minus 3 and 2n minus 1. So I'm just going to make these exponents consistent. So I'm going to make it 2n minus 3. And the reason why that works is because of this n minus 2 here. Sorry, that should have been an n minus 2. So when we do that, what we get is this still stays the same, but we can just do some simplification here. 2m minus 1 and minus 1 gives us minus 2. And we have in the denominator, we have 2m minus 1. And also I should just include a plus here. So there's a plus there. This is not a multiplication. So 2m plus 2n minus 1 and minus 1 is going to give us minus 2. So we can divide the numerator and the denominator by 2. And when we do that, we get m minus 1 divided by m plus n. Now we apply this second result to this integral. And when we do that, we get integral from 0 to pi over 2. And then we're going to have sine of 2m minus 3 of x times cos now of 2n minus 1. But remember now it's n minus 2. Yeah, so it's going to be 2n minus 1 minus 2. So we're going to be left with 2n minus 3 of x dx. So all I've done is instead of n, I've put in 2n minus 1. So also we shouldn't forget that there's this n minus 1 times m plus n term here in front. So I'll just write it next to it. So it's going to be n minus 1, but however, n is actually 2n minus 1 because that's according to the beta function. Let's not forget that. Beta function is 2n minus 1. So that's what we're going to put here. We have 2n minus 1, 2n minus 1, and then minus 1 divided by m plus n. So it's actually 2m minus 1 plus 2n minus 1. So it's the same thing. So it's 2n minus 1 plus 2m minus 1. So we can just write these results to make it look just a little bit more nicer. And when we do that, we now have m minus 1, and we can write this 2n minus 2. Again, we do the same thing. We can cancel out all of these terms here. This 2's, we can cancel out the 2's. And when we do that, we get m minus 1, and we have n minus 1. And now this is divided by, we have sorry, there should be a minus 1 there as well. So we have m plus n minus 1. And also we're going to have m plus n minus 2. So the reason why we have m plus n minus 2 is because of this term. And this is multiplied by 2 times the integral from 0 to, well, essentially what this is just the beta function of m minus 1 and n minus 1. This is easy to see because of this 2m minus 3. So this 2m minus 3 is just 2 into m minus 1 minus 1. So 2 times minus 1 is minus 2, and minus 2 minus 1 is minus 3. So we're making some progress towards some kind of general result. So this is the beta function of m and n. So what I'm now going to do is I'm going to replace this m and this n with m minus 1 and n minus 1. So I have beta times into m minus 1 and n minus 1. And when I replace these terms, I get m minus 2 and then n minus 2, because m minus 1 minus 1, so it's m minus 2. And then I have m plus n minus 1, m plus n minus 2. So that's going to just give me m plus n minus 3, and then m plus n minus 4. And this is multiplied by the beta function now of m minus 2 and m minus 3. Sorry, n minus 2. And then I can rewrite this, for the next one. That's m minus 2 and then n minus 2. And then what that gives me is going to be m minus 3 times n minus 3 divided by m plus n minus 5 and then m plus n minus 6 times the beta function of m minus 3 and n minus 3. So we can see that we are developing a trend here. So if we now take this beta of m minus 1 and n minus 1 and substitute it inside our first equation here, then essentially this entire term is going to be replaced there. And then in that term, we will have beta of m minus 2, n minus 2. And then in that term, we can replace this with this third equation that we have just written, and then we can put that in here. So we can see that we can carry on doing that. And then if we carry on doing that, let's just write it for, beta of mn. What we're going to have eventually is we're going to have m minus 1, okay? Then we're going to have m minus 2, then we're going to have m minus 3, and then we're going to have n. So we're going to have n minus 1, n minus 2, n minus 3, and so on. And in the denominator, it's going to be the same thing. We're going to have m plus n minus 1, m plus n minus 2, m plus n minus 3, and it would carry on like that. And the last term we had written here was beta of m minus 3, n minus 3. That's 3 and n minus 3. So we can see our trend developing. And if we just, generalize our trend, then what we see is that we get that the beta function of mn is equal to just m minus 1 factorial, because that's what it is, m minus 1, m minus 2, and so on, multiplied by n minus 1 factorial divided by m plus n minus 1 factorial. So perhaps I've skipped a few subtleties in this explanation, but nevertheless, you can see how we have approached this general result. So it's quite straightforward. So if we have the beta function of m where m is 3, let's just make it 5, where m is 5 and n is 3, then what it means is that we have m minus 1, so it's 5 minus 1, that's 4 factorial, n minus 1, so that's 3 minus 1, that's 2, that's 2 factorial, divided by m plus n. So we have 5 plus 3, which is 8. 8 minus 1 is 7. So that's 7 factorial. So this is it. This is the general result of the beta function. And this is, of course, defined as the integral from 0 to 1 of x to the power m minus 1. So that's x to the power 4 multiplied by 1 minus x to the power n minus 1. N is 3, so it's 3 minus 1 is 2. So it's to the power 2 times dx. And this is what is equal to 4 factorial times 2 factorial divided by 7 factorial. So this is the general result. This is how the beta function can be computed in terms of the general result. So just other one thing that we can mention is that what if m and n are equal to half? So we want the beta function of a half and a half. So this we can use the definition in terms of the alternate form we had derived using the trig functions. So it's 2 times the integral from 0 to pi over 2 of sine 2m minus 1 of x times cos to the power 2n minus 1 of x dx. So here m is half, so we have 2 times a half, and 2 times a half is 1, 1 minus 1 is 0. So this is sine to the power 0. And then again, 2 times a half is 1, 1 minus 1 is 0. So anything to the power 0 is 1. So we have the integral of 1. So when we integrate 1, we just get theta. So we have 2 times theta from 0 to pi over 2. So this is just going to be pi over 2, and then 2 times pi over 2 is just pi. So the beta function where m and n are both half just gives us the result pi. So this video essentially defined what the beta function was, and we saw that it's equal to x to the power m minus 1 times 1 minus x to the power n minus 1. And what we did was then derived a general result, a general formula to evaluate the beta function for different integers m and n. And how we had done it was we did a substitution where x is equal to sine squared theta. And once we did the substitutions, we then used the reduction formula, the general result of the reduction formula, and wrote the beta function using those reduction formulas. And we had seen that all of this simplified to m minus 1 factorial times n minus 1 factorial divided by m plus n minus 1 factorial. And this is how we can compute the beta function for different integers of m and n. So thank you very much for watching.